Okay, party people, let's do some practice problems. So we're going to use graphs to find the total distance traveled. Let's look at this first example in your notes packet. So it says the velocity time graph for a train journey is illustrated in the graph alongside. So note that this is going to be time, and then over here is going to be kilometers per hour, which is going to be the velocity. Okay. We want to find the total distance traveled by the train. So what we're going to need to find here is the area under this curve. We are going to have to break this guy up into composite figures. Do you remember doing these in, I don't know, maybe like geometry or something, right? You're going to break, I don't know how to take the area of something that looks like this, right? But I'm going to break it up into figures that I do know how to take the area of. So like this guy would be a triangle. This guy would be a rectangle. This guy would be a parallelogram, throwback. This guy would be a rectangle. And then this guy would be a triangle. Actually, if you don't feel like dealing with parallelograms, this one could also be a rectangle with a triangle on top, like a tiny little hat. Okay, so here we would take the area is equal to, the area of a triangle is equal to 1/2 base times height. So we have a base of 1 and then a height of 1, 2, 3, 4, 5, excuse me. So we would have 5 divided by 2, which is going to be 2.5. And then here we have area is equal to base times height, or we could just count the boxes, right? 2, 4, 6, 8, 10. 1, 2, 3 boxes here, 3 boxes here. This one is going to have a height of 2 and a base of 1. So we're going to take 2 divided by 2. That's going to give me 1. And then here we've got a base of 1 and a height of 3. So that's going to be 3/2 or 1.5. So if you wanted to add those all together, the total area under the curve here is going to be 21 kilometers. That would be the total distance traveled as well. So you saw here that it was like super easy to add up things that look like this, right? You can just break it up into figures that you know how to take the area of. But what if you're trying to find the area of something that's like more swoopy? It's going to be a little more difficult, right? So let's look at practice problem number 1, okay? You're going to pause the video and you're going to solve this one on your own and then see if we get the same answer, okay? Okay, did we get the same answer? We did. However, I didn't put in my units. There we go. All right, so the runner traveled 110 meters. Let's look at this one here, okay? It says a car, this one is a little less straightforward, so we're gonna go through it together. A car travels along a straight road with the velocity time function illustrated. What is the significance of the graph above the t-axis? So above the t-axis, all velocities are positive, aka the car is moving right. So we could say all velocities are positive. Car is moving right. Why? Because all y values are all outputs of the function are positive. Okay. What about things or what about parts of the graph that are below the t-axis? Below the t-axis. Well, that means that velocity is negative. The car is moving left. Okay. So now part B says find the total distance traveled by the car. So total distance traveled by the car. We're going to set up integrals where we split it up by the roots and then we subtract the negative parts to make the area positive. Okay. So instead of setting up integrals, this is actually a nice little picture and we can just kind of count the boxes, right? We can do the area of a trapezoid, which is the average of the two bases, right? So 3 plus 1 is going to be 4 divided by 2, which is 2, times the height, which is 3. So that's going to be 6 units here. And then same idea, this is a trapezoid, but he's below the x-axis. So we have the average of the two bases times the height. This one's going to give me an area of 2 down here. So if we're trying to find the total distance traveled by the car, we are going to do 6 minus -2, and that's going to give me 8 kilometers. Okay. And then C, find the final displacement of the car from its starting point. So final displacement is going to be distance from the origin, okay? So let's kind of think about it like this, right? We have a final displacement of, let's see, we started with 6. We moved 2 units to the right. We ended up with a positive 4. So that would just be 4 kilometers to the right of the origin. And that would be our answer for C, finding the final displacement. Final displacement. Let's talk about the graphical distance between distance and displacement, okay? So when we're given a graph and we're trying to find the total distance, what we're doing is between here and here, right? This is going to be time 0, time 1, and time 2. Between time 0 and time 1, we are finding the area or the area under the curve of this guy. And then we are adding it to the area under the curve of this guy. However, he's negative, so what we're going to do is subtract his area, because that will then give us a positive area. Okay. What we're essentially doing is flipping this guy above the x-axis when we take the absolute value and then adding the two things together. So we would get an area of 2 here, an area of 2 here, and then whatever this area comes up as, and we would add them all together and get our total positive distance traveled, right? And then what we're doing over here with displacement is we want to keep this bottom portion negative because he's telling us about all that left motion, right? This is right motion to the right of the origin. This is motion to the left of the origin, and we want to keep him negative so we can see where this particle finally ends up after all of his motion is done, or at whatever time we end up evaluating it at, right? So if we found the area of this guy up here, it just happens to be 13.5. And then we found the area of this guy down here below the x-axis. He would happen to be at 4. We want to keep him negative. So we would subtract this 4 from the top, the positive portion. And that would give us a total displacement of 9.5 units. So that means that this guy started at the origin and he moved to the right of the origin for 13.5 units. Then he turned around, changed direction, and came back 4 units and ended up somewhere here, which ended up having to be 9.5 units to the right. Okay, so this is just showing motion along a straight line, but as a graph. Okay, and we want to keep those negative or left movements negative so that way we can account for the backtracking or the motion back towards the origin. Okay, so let's see, we have from here to here, from time 0 to time 2, we would just take the entire integral of that guy. Okay, and that would give us the displacement. Okay, we're not messing with the signs like we are over here to keep things positive. So the big difference is with displacement. Remember that displacement refers to your change in position. I feel like people don't really want to be read to, so I'm just going to give you like a few seconds to read this part here, and then all the way down to the bottom, and then we'll meet back in like 3 seconds, okay? So you can pause the video, and then we'll pick right up when you're done. So when you think displacement, think position along a path, okay? So when we use calculus to find total distance traveled and displacement, we do stuff like this. Just check out example number 3. A particle P moves in a straight line with velocity function v of t equals t squared minus 3t plus 2 meters per second. Answer the following without using a calculator. Okay. A, how far does P travel in the first 4 seconds of motion? So what we're going to want to do is find the roots of this guy. So we know how to break up the integral, okay? So how far does P travel? It's going to be total distance traveled in the first 4 seconds of motion, okay? So we've got T, I'm not going to do math in Rainbow. It's hard to follow. Okay, here we go. T squared minus 3t plus 2 equals 0. We would get T minus t minus 3, and then t plus 1. And then that would give us a, nope. There we go. That would give us the roots. So we've got t equals 2, t equals 1. All right, cool. So these are going to be our roots, right? So we've got something that looks like this. He's a parabola. He's got roots at 1 and 2. 1 and 2, and he looks like this. So we've got a little bit of a negative portion here, okay? And then we have a positive portion here, and then we're ending at 4. So it's just going to go from 0 to 1, 1 to 2, and then 2 to 4. Okay, wow, all right. So we've got 0 to 1. That's going to be a positive. And then we have minus, because this portion is located, oh, I forgot the dt, sorry. And then we're going to have minus, because this portion is below the x-axis, from 1 to 2. And then we're going to be adding that last little piece that's above the x-axis, from 2 to 4. All right, cool. Oh, my son is awake. Sorry. Okay, so now we've got the function in there. So we've got, let's just find the antiderivative of this guy right here. We've got 1/3 t cubed minus 3t squared divided by 2 plus 2t. All right, and we are evaluating him from 0 to 1 minus and then he's a positive portion, so we're going to add this last piece here. All right, now let's see what we've got here. So if this is a 1, we're going to have 1/3 minus, this is going to be 3/2 plus 2, and then this whole piece is a 0, so he's going to disappear. Minus, now we have 2 cubed, which is 8 divided by 3, 8/3 minus t, so that's going to be 4, and that's going to be 12 divided by 2, which is going to be 6 plus 4, and then this whole guy is going to be minus 1, so that's going to be 1/3 minus 3/2 plus 2. Okay, integrals by hand, aren't they fun? And then now for the last part, we have, okay, we've got 1/3, 4 cubed minus 3 times 4 squared over 2 plus 2 times 4 minus Yeah! Actually, these are all in like big giant parentheses. Okay. Minus 1, so it's going to be 8 over 3 minus 2, that's 4, 12 minus 6 plus 4. Okay. All right. And then now we've got 1/3 minus 3 over 2. It's going to give me okay, so this whole guy, for the purposes of just keeping things, keeping track of things. Okay.